Hello friends, welcome to my YouTube channel JK Academy India. In this video, we will discuss about the working principle of DC motors, torque and EMF equations of DC motors and the types of DC motors. So let's start the video. First one is the working principle of DC motors. The operation of a DC motor is based on the principle that when a current carrying conductor is placed in a magnetic field, a mechanical force is experienced by it. The direction of this force is determined by Fleming's left hand rule. In case of generator and in case of transformer, we apply Fleming's right hand rule, but in case of motors, DC motors, we apply Fleming's left hand rule. Its magnitude is given by the relation F equals to BIL Newton. The force experienced by the rotor is given by the B flux density of the field. I is the current flowing through the conductor and L is the length of the conductor. For simplicity, consider only one coil of the armature placed in a magnetic field produced by a bipolar machine. So this is N pole and this is S pole. Direction of the magnetic field is towards right. A conductor of L length is placed here. When DC supply is connected to the coil, current flows through it, which sets up its own field. Now, when we supply this conductor, it will produce a magnetic field, and by the interaction of the two fields, one field of these poles and other field created by the conductor. So by the interaction of these two fields, main pole and the coil, a resultant field is set up like this. This is the resultant field. The tendency of this is to come to its original position. Means this field will try to align in this direction. That is in a straight line, due to which a force is exerted on two coil sides and torque develops which rotates the coil. So this is the working principle of DC motor. Now back EMF. It has been seen that when current is supplied to armature conductor placed in a magnetic field, here in this figure also, a torque develops and the armature rotates. Simultaneously, the armature conductors cut across the magnetic field and an EMF is induced in these conductors. The direction of this induced EMF in the armature conductor is determined by the Fleming's right hand rule. Here, to find out the EMF induced in the conductor, we will apply the Fleming's right hand rule, not the left hand rule. Left hand rule is to find out the rotation of the motor. It can be seen that the direction of this induced EMF is opposite to the applied voltage. Here, the sign of applied voltage is positive, here is negative. So, The current flowing through it in this direction, and this is the back EMF or EMF induced in the armature, is in upward direction. So it can be seen that the direction of the induced EMF is opposite to the applied voltage. That is why this induced EMF is called back EMF. The magnitude of this induced EMF is given by the relation Pz phi n by 60A. Therefore, EB is proportional to flux and the rotation of the armature. Also, speed is also proportional to back EMF divided by flux, shows that the speed of the motor is inversely proportional to the magnetic flux. A simple conventional circuit diagram is shown here working as a motor. In this case, the supply voltage is always greater than the back EMF. V is greater than EB. Therefore, the current is always supplied to the motor from the mains, and the relation among the various quantities will be EB equals to V minus IaRa. IaRa is the voltage drop in the armature and V is the supplied voltage. Significance of back EMF. The current flowing through the armature is given by the relation Ia equals to V minus Eb upon Ra. When mechanical load applied on the motor increases, its speed decreases, which reduces the value back EMF. As a result, the value of E minus Eb increases, which consequently increases armature current. Hence, motor draws extra current from the mains. The back EMF regulates the input power as per the extra load. So whenever mechanical load applied on the motor increases, speed decreases, and because of that EB reduces. So as a result, V minus EB increases, which consequently increase armature current. Hence the motor draws extra current from the mains. Thus the back EMF regulates the input power as per the extra load. Electromagnetic torque developed in the DC motor. Electrical power which is supplied to a DC motor is converted into mechanical power. The conversion of power takes place in the armature. So the power developed in armature is given by E into Ia equals to omega into Te. T is the torque developed in the armature. Also, EIA equals to 2 pi n upon 60 into Te, because this speed can be written like 2 pi n upon 60, because this is the radian per second and this is RPM. So the torque will become Pz phi n upon 2 pi a Newton meter. For particular machine, the number of poles, number of conductors per parallel path, Z by A are constant. Therefore, T equals to K phi Ia upon 2 pi, where K equals to Pz by A, which is a constant. The constant K for a given machine is the same for EMF equation as well as for torque equation, as well as the torque equals to K2 phi Ia, where K2 is nothing but Pz upon 2 pi A is another constant, or we can say that torque is just proportional to flux and the armature current. Thus, it is concluded that torque produced in the armature of a DC machine is directly proportional to the flux per pole and the armature current. The direction of electromagnetic torque developed in the armature depends upon the direction of the flux or magnetic field and the direction of flow of current in the armature conductors. If either of two is reversed, the direction of the torque produced is reversed and hence direction of rotation. But when both are reversed, the direction of torque does not change and rotation will remain same. Shaft torque. In DC motors, whole of the electromagnetic torque Te developed in the armature is not available to the shaft. A part of its own is to overcome the iron and mechanical friction or windage losses. Therefore, shaft torque TSH is somewhat less than the torque developed in the armature. Thus, in case of DC motors, the actual torque available to the shaft for doing useful mechanical work is known as the shaft torque. Now, what is BHP? Brake horsepower. In case of motors, the mechanical power HP available at the shaft is known as the brake horsepower or BHP if TSH is the shaft torque in Newton meter and N is the speed in RPM, then useful output power equals to omega TSH will be this, and output BHP will be 2 pi N TSH upon 60 into 735.5. So 1 HP equals to 735 watt. This is the relation between HP and watt. Types of DC motors. On the basis of connections of armature and their field winding, DC motors can be classified separately excited DC motors. Diagram is shown for the DC motor. We will see, and the back EMF produced is given by V minus IARA armature drop, and this is the carbon brush voltage drop. In self-excited DC motors, shunt motors, the conventional diagram we will see on next slide. Important relation: current in the shunt field can be written by V by RSH, where armature current equals to IL minus ISH. So the back EMF formula will be like this: V minus IARA, and this is carbon brush drop. These are the two circuits. This is the separately excited DC motor. Here IA equals to IL, and here this is the self-excited DC shunt motor. IA equals to ISH, current flowing in shunt winding, plus IL. This is IL and this is IA armature. Next is the series motor. Its conventional diagram is shown here. In case of series motor, IA equals to IL. There is no change. So the back EMF formula will be like this. It will remain same, but here Along with the armature resistance, we are considering the series resistance to count the total voltage drop. In case of compound motor, this is the circuit diagram. Here the IL is equal to IA plus ISH. So in this case, back EMF formula will be like this: compound motor, RA plus RAC and 2 VB. In all above equation, the brush voltage drop VB is sometimes neglected since its value is very small. The compound motor can be further subdivided. One is the cumulative compound motor. In this motor, the flux produced by both the windings is in the same direction. So phi R total flux will be phi SH and phi AC. The flux produced in the shunt field, flux produced by the series field. In differential compound motor, the flux produced in the field winding is opposite to the flux produced in the shunt winding. So the resultant flux will be phi SH minus phi AC. So thanks for watching.